All right, everybody, it's just about 10 o'clock, so we will get started. I don't know if you can see my shirt at home. I'll try to lower this camera. This is a SKYWARN shirt that was given to me at a previous office I worked at. This was up in the upstate New York area. So I thought, usually I wear a polo shirt to these classes, but I thought, hey, I'm doing the training from home. Why not mix it up a little bit? So I've got my SKYWARN shirt on me today. So my name is Eric Hayden. I'm a meteorologist with the Weather Service in Morehead City. Very excited you could join us. We've done these virtual classes for a couple years now, but this is the first time we've done an advanced class in quite a few years. So this is something we're really excited about, and we welcome any feedback that you have for us. You'll be able to download this presentation eventually from our website. Again, we've done these classes for a while. Given our current situation, we've just expanded it. So a normal year, we might have 20 classes in a season. 17 of those are in person, whereas only 3 are online. With what's going on right now, we just expanded our virtual class offering. You'll get a certificate of completion here soon. Make sure you registered with a good email. Sometimes I get some bounce backs. So if you put in an email with a mistake and you don't get a certificate, that's why. So just follow up with me after the class itself. This is an advanced SKYWARN class. By design, all of our classes outside of this are for everyone. We try to keep them basic, simple, to the point. This is not this class. This is in depth, and some of it might be over your head. So if you haven't taken the basic class, don't worry about it. We do like you to do that first, but after this, kind of go back and look through our basic class. We've got it on YouTube, and you can also scroll through the PDF. The reason why I mention that is we really try to emphasize reporting with our basic class, whereas this gets into the meteorology just a little bit more. So I want to make sure folks see both of them by the end of the next couple days. So speaking of this, our advanced class is a follow-up to the basic spring class, which is severe weather. We do have a winter class, which focuses in on ice and snowfall reporting. And then again, you saw from the schedule that we have a flood and tropical SKYWARN. Our goal is that you're a year-round spotter. Luckily, we don't usually have tornadoes and large hail exactly where you live, but we want you to get in the habit of reporting rain and snow so that if you do have severe weather, it's second nature for you to report to our office. All of our information is on our website. That's weather.gov/Newport. We post that at the top. And again, our goal is that you're a year-round spotter, that you get involved in the COCO-RAWS program, and it's second nature to you if we have any bad weather. One way you can keep informed is our YouTube page. It's youtube.com/NWS Morehead City. And I should mention, as I follow up with you via email, that certificate, I'll provide all these links. So don't think you got to jot all this down. On our SKYWARN page, we're very proud. In addition to the current schedule and when to report, we also have the option to see, training via YouTube. So on the far right-hand side of the page, we have a section called YouTube Training. If you click on that, there's a 7-part series for the basic SKYWARN, and we also have the winter SKYWARN as well. So a lot of information for you that you can do at your own pace and at your own time. Now, as far as this webinar goes, since I can't see you in a class, we want to make it as interactive as possible. So if you've got a question, raise your hand. I'll try to look at that throughout the class so we can kind of get to it. If not, just ask it through the webinar itself, and we'll get to those at the end. If you raise your hand and you have a mic, we can hear from you verbally. Otherwise, you can do it through the program itself. We've done this for a couple weeks now. It's been really successful, so I think everybody will be able to figure that out. So some of the topics we'll be going over, very, very briefly, we want to review spotter procedures. That's especially for those that haven't taken a class in a while, and perhaps you skipped over the basic part. We want to make sure we get that out of the way. This is an advanced class, so we're going to go in depth on dual pole. What is CAPE and instability? Wind shear, supercell thunderstorms, tornadoes, squall lines, radar reflectivity, and velocity. So again, this is more meteorology, but this is kind of our gift back to you to go deeper into the science. A little bit about the Weather Service. We're out of the Newport office, which is across far, far eastern North Carolina. I like to tease people, if you go as far east in North Carolina before you hit the ocean, that's our area of coverage. You'll notice we have over 100 offices in the country itself. We have some folks that are joining us all across the country, and that's great. After this class, I want you, we're going to forward your information to your local office, because I'm going to go over how to report severe weather, and those numbers won't apply to you. I'll explain what that means here in a second. As far as our own office is concerned, I mentioned that we cover kind of the eastern quarter of North Carolina. We do extend out into the ocean. That yellow shaded area is out to 20 nautical miles. Those areas that are not shaded up toward Raleigh or down toward Wilmington, that's covered by our surrounding sister offices. So all of the country is covered by a local office that does those warnings for you. We are open 24/7. The main mission of the Weather Service is the protection of life and property. So we're here when the weather is bad. This is our local office during Hurricane Florence. We're in a reinforced building. The lower picture on the left shows the hurricane shutters. It's a brick building. Some of us were here up to a week during Florence because of damage to our own homes. So we stay here. We've got backup procedures. If we have a communications issue or something happens to the building, we can transfer control over to a sister office. So lots of backups in place to serve you no matter what's happening with the weather. Going to briefly touch on our website. Our local site is weather.gov/Newport, but keep in mind, no matter where you live in the country, if you just go to weather.gov and then click on your area of interest, that will send you to your local Weather Service office. And you can get a lot of forecast information. As a big time gardener, I love this website. It gives you a brief forecast at first. The icons tell you the high and low. The text will tell you percentage of rain and also wind speeds out to a couple days. Very, very useful forecast. On the website itself, you can get more detailed forecasts by going to the hourly weather graph or the graphical forecast farther down on the page. So that's a little bit about who we are as the Weather Service. Wanted to briefly touch on our website because that's where you can get a lot of the good information in terms of forecasts from the local office itself. As far as SKYWARN goes, it's a national volunteer program run by the Weather Service, and the main goal is to provide ground truth reports to the Weather Service of significant weather. You really help us, confirm what's happening or reinforce perhaps that it's not as bad out as what we're thinking. These assist us in our warning decision process. You help us gauge how bad a storm is. If you call in a hail report, then I know exactly what's happening in your local town. I can compare it to the radar and see how that matches up. Let's say you add information, tornadoes on the ground. We've got baseball size hail. By us adding that information to a warning, that puts a local town into the warning, says it's already happening. And think about how often we get these warnings, and you might say, that's not going to happen to me. But when you see that another town just to the west of you is actually experiencing this, you're going to take that information much more serious. A quick overview of what to report before we get into the nitty-gritty of the class. We want to know about tornadoes and funnel clouds. Remember from our basic class, they have got to have rotation. We want to know about flooding, any type of storm damage, any size hail. Please do not use marbles to measure hail. You want to either use a ruler or you want to compare it to a known coin size. Rainfall amounts are useful. If you have a rain gauge, that's very helpful. And as far as wind speed or damage, knowing what is actually damaged, how many trees are down, are there branches, large branches, things of that nature, to let us know what specifically is happening where you live. How can you make your report? Our most preferred way is the 800 number. Again, the 800 number in email that I'm going to talk about in a second, that is specific for Eastern North Carolina. So you folks out in California or New York that might be on the call, the procedure is the same. But you're going to need a different number to call your local office, and that's what we'll follow up with you here in the coming weeks. The procedure is the same, no matter where you're a spotter. Who are you? What you saw, where you saw it, and when. It's very, very important the when, because if you tell us you had a tornado and you just came from seeking shelter and it was actually 20 minutes ago, we're going to be confused because we're going to look at the radar and it's not going to match up. So tell us when it happened. Identifying yourself is important. And the 800 number is preferred because we can ask you questions and we answer this 24/7. So there's a lot of different ways to report to us, but by far the most popular way for us is that 800 number. We do offer an email, and again, this is specific to Eastern North Carolina. This is not for the whole country. You'll have different numbers and emails depending on what your local office does. The email is a nice follow-up. Let's say you make a hail report. We want you to call us, and then if you took a picture or some video and you want to send it to us, use our email. Same procedure, who you are, what you saw, where you saw it, and when. By having that procedure, again, when the weather gets crazy, we want to know about the reports right away. We don't want to wait for them. So having that concise report is very, very important. So that was a little bit about who we are and just a brief overview of reporting procedures. I encourage you, again, please take the basic class if you have not done so already. It's a great class, but we really hammer home what we want reported. And that's the biggest part of SKYWARN. It's not being the best meteorologist or knowing the most science. It's simply calling your local office when you get severe weather. Now, the bulk of the presentation is going to be our advanced class. I welcome any feedback. This is the first time for me, so you know, some of these slides we're going to go over and we're going to change for future classes, depending on how they go. We're going to talk a little bit about the radar. The radar itself, the diagram on the left, that triangle shows the radar itself. When we send out a pulse of radiation into the environment, we have a low scan of the radar, which is 0.5 elevation above the horizon. And then we can actually tilt the radar up and down, but we can never go back lower than 0.5 degrees. And because of that, we can see a lot of the atmosphere above us. So on the picture at the bottom, and the area I'm circling, that's what the radar is scanning. But you'll notice because the Earth is curved, that's what this green line represents at the top, even at the lowest angle, as it gets farther and farther away from the radar, especially out toward 100 miles, it's very high up in the atmosphere. It can be up as much as 7,500 feet. So the radar does not see things close to the ground the farther it gets away, and that's where spotters and GOES 16 satellite and other things can help fill in the gaps from where the radar may struggle. A couple principles with radar before we go on to the dual pole aspect that we upgraded to. It's been quite a few years now. Time is passing by pretty quickly. On the picture on the right is our radar. It's actually a gigantic satellite dish. So if you ever see a local office, it looks like a giant soccer ball. That's the protection of the radar. But what it actually is a big satellite dish, and it sends out a pulse of radiation, and it bounces off targets, and then it scatters, and the pulse comes back to the receiver. Most of the time, it's just listening for these pulses if they come back. If they never come back, it's not hitting insects or birds or rain, hail, or snow. It's clear. If it gets bounced back, you see what you see on the left, which is the radar reflectivity mode, where you see these darker yellows and reds. That's higher reflectivity. We're getting more of that scattered pulse back. So that's the reflectivity mode of the radar. As we tilt the radar up, depending on what we see, we can see higher intensity, and that can indicate things like hail. This is a cross section in the lower right. As we go up in the atmosphere, we're increasing with height, and this white shaded region is at the very least heavy rain, but as it gets up toward 20 and 30,000 feet, that's above the freezing level, so that's an indication of hail. The other way we see it on radar, again, very, very intense reflectivity here. The pink shading, that is an indication of hail. And then we can see some reflectivity on the backside of the storm. That's called a hail spike. And that is an indication, we used to call this a three-body scatter spike. And that can show us that there is hail produced with the storm itself, and it could be large. So we talked first about the reflectivity. That's what you're probably most used to. Darker colors mean heavy rain, heavier snow, things of that nature. What you may not be used to is this mode of the radar. The reason why it's called a Doppler radar is it can detect particles moving toward and away from the radar itself. Now, we don't actually see tornadoes on a radar, but what we can detect is strong rotation. On this graphic on the right, particles moving away from the radar itself appear as red. So in this case, everything here, the radar is down to the southeast here. Everything in red is moving away from the radar itself. So all this red area is moving away from the radar, and it's a little off the screen, but we'll just pretend the radar is this circle down here. It's actually off the screen down toward Newport. Now everything green on this radar map is actually moving toward the radar site. So that's how we can see how the wind is flowing in the atmosphere. So right here we have a convergent area based on what the radar is seeing. But if we have an area right here where you have greens and reds right next to each other, that's showing very strong rotation. In this case, this was an EF3. That's about as bad as it gets here in eastern North Carolina, 2014 near Chakawinity. Again, that shows the Doppler radar. Red is away, green is toward, and if you've got them co-located with a thunderstorm, that can potentially be a tornado. So on the left is the reflective, or is the velocity. So again, red is away, green is toward. And this area right here, we've got strong rotation. And then if we have the reflectivity to support it, that could very well be a tornado. In this case, we've got a hook echo co-located with the rotation. And unfortunately, that was one of the worst tornadoes we've seen here, certainly in recent memory, but especially for eastern North Carolina, that's a pretty big one, an EF3 in 2014, late April. So that's basic radar. Reflectivity shows us the intensity. The velocity shows us movement of the wind. We made an upgrade, and I'm going to lose track of time now. It might have been 2012, 2013, 2014. The years are kind of passing by, but it was a little while ago that we did an upgrade in the Weather Service, and it was a dual polarization. I'm going to go back one. Looks like my presentation. Okay, it froze up there for a second. I want to make sure that you've got the animation here. So with our old radar, is the example on the right. It sent out, again, a beam of radiation. It would bounce off and scatter and come back to the radar, only in the horizontal plane. With dual pole, we added the element of also seeing in the vertical. And this helped us a lot with determining what the drop size was. This could help with rainfall detection, hail size, and also different types of debris in the atmosphere. I'm going to kind of go through these terms kind of quickly, and I want to back them up with images because I don't like just a lot of text. But we got a couple new products with dual pole. One is differential reflectivity. It shows us a difference in return power. One that we use a lot is correlation coefficient. This is awesome for determining the likeness of a particle. So if you see all one color, you know it's rain or snow or what have you. And this can really help in the wintertime to determine where is the rain snow line and where the mixed precip might be. And another one is specific differential phase, and this helps determine the amount of liquid in our storms. We do have other type of scatterers. A lot of times people think of just rain or snow or hail, but the radar can pick up anything that can bounce back, that radiation to the radar itself. This could be birds, insects, anything that flies. So sometimes you'll see or you'll hear us say that there's a lot of ground clutter on the radar. A lot of times this is insects and birds and other biological scatterers that get bounced back toward the radar. Sometimes it can be mixed precip. So it could be an indication of hail, sleet, and it could unfortunately also be an indicator of debris up in the atmosphere in terms of trees or parts of buildings. So that's where we use the correlation coefficient a lot. If we've got everything uniform, so on the far right, if it's rain, all snow, no matter what it is, if it's all pretty uniform, we have a very high CC, around 0.97 or higher. Once we start to get some mixed precipitation, that value will drop down to 0.8 or 0.97. That could be where some hail's mixing in or some sleet. And if it's below 0.8, it's a lot of mix of different things, and it could be birds or insects. These values mean nothing to you until you start to see some images. When you see the images, it all makes sense. So on the picture on the lower left, all of this area, whatever it is the same. So if we know it's a cold winter day and we're 20 degrees, we know it's all snow. If it's a warm summer day, we know it's all rain. So whatever that is in that area, it's all the same because the CC is greater than 0.98. Here in the edge might just be some lighter precip, but it's non-uniform. So that's the difference between the two. On the example on the right, again, a lot of mixed here. It's not all uniform, so it's not as consistent. So this is what I mean, this area here with consistent CC can tell us it's all rain, all snow, whatever's going on in the environment. Think back to the biological scatters. If you've ever seen a radar image, you might see this, especially at night. Let me go back one. So all these areas here are rain, where you have the higher reflectivity. This is all rainfall. But where you have these big donuts or circles around the radar site, this is ground clutter. A lot of times in the case, birds, could be migratory birds, it could be insects. That is all ground clutter. It would show up better as an animation, and you could see that the rain is moving and the ground clutter doesn't move much at all. The correlation coefficient can show us this. Again, here's rain, a consistent value above 0.9. And you can easily pick out those areas of rain. So the point of these slides is to show, before we could kind of determine it from the reflectivity, and we knew for the most part, but with the correlation coefficient, it really jumps off the screen even all that much better. Another way, unfortunately, that the correlation coefficient can help us is after a tornado is on the ground. So this is not so much for warnings. This is to perhaps added detail to a warning that's already in place. On the upper left, here's our hook echo. So again, very, very high reflectivity wrapped around, showing that rotation in the thunderstorm. On the right is our storm relative motion. Again, red is away from the radar site and green is toward the radar site. So where you have it together, you have very, very strong rotation. So that's what we see in reflectivity and also the velocity. But then when we add the added feature of correlation coefficient, if that is co-located with an area of high reflectivity and strong rotation, this is likely debris. It could be trees, it could be parts of buildings, but this is a non-uniform area because of that low correlation coefficient below 0.8. We can't just willy-nilly look at this. It's got to be co-located with strong reflectivity and strong rotation. But that can, if we have a warning out, we can add that tornado has been confirmed based on those three things. So that dual pole upgrade helped us a lot. I didn't go into it too much, but because of the drop size that it can measure, the accuracy of rainfall measurement estimation from the radar got a lot better. In addition, hail size and things of that nature got a lot better with the dual pole upgrade. Phenomenal stuff in the Weather Service. We continue to advance through the years to try to make our forecast and warnings as accurate as possible. So now we're going to talk a little bit more about thunderstorms. If you took the basic class, you might say, hey, Eric, we already did winds and rain and hail and tornadoes. We're going to do the same thing, but we're going to take it a step further, go more in depth on each one. I know we talked about shear. I know we talked about instability, but now we're just going to go a little bit more in depth on each principle. Just to recap, if you missed the basic class, our definition of a severe thunderstorm is 58-mile-per-hour winds or greater and 1-inch hail or larger. Statistically, that's about where we start to see damage. You'll notice that lightning is not in a warning, or we don't issue warnings for lightning. Lightning is very dangerous. We're usually in the top 5 for deaths in the country in North Carolina for lightning. But if we issued a warning for every thunderstorm, we would be doing that 4, 5, 6 days out of the week sometimes in the summertime. So from our basic class, we talked about instability, we talked about moisture, we talked about having a lifting mechanism, and we talked about wind shear. We'll briefly cover those topics, but again, since it's an advanced class, we're just going to go a little bit more in depth. If you think back to our demonstration in the class of the basic class, instability is really fuel for thunderstorms. It's the difference between warm and cold air. The example on the left, warm air can actually hold it's less molecules per area, so it's actually lighter and it can hold more moisture. If you have a difference in temperature, if you're very warm at the surface and as you go up it gets very cold quickly, that's unstable. That air is going to naturally rise. And instability is fuel for thunderstorms. The higher the instability, the greater potential you have for those thunderstorms, and potentially severe if everything sets up. This is what I'm getting at with the atmosphere. Again, relatively warm air is less dense. It naturally is going to want to rise where cold air wants to sink. So the warmer you are, the more buoyant your atmosphere is. It has more fuel and more instability for those storms to form. One way we measure instability in the atmosphere is something called CAPE, a convective available potential energy, if you're keeping score at home. We love our acronyms in the Weather Service and just weather in general. It's a measure of buoyancy in the atmosphere. CAPE's 500 to 1,000, we can usually get thunderstorms. They could be severe, especially if you got some shear, and we'll talk about that in a second. 1,000 to 2,500, more likely to produce severe thunderstorms, maybe even some tornadoes. And above 2,500, that's where we can have some major types of severe weather, especially if we have severe weather. Here in the south, where we have a lot of humidity and moisture, we commonly can have CAPEs above 2,500. The problem is we might not have the shear or the forcing mechanism to generate severe weather. So our CAPEs tend to be pretty high in the summertime, but we're missing some of those other ingredients such as lift or some type of trigger to set things off, or maybe it's too dry higher up in the atmosphere to get things going. This is an example of CAPE. This is from a meso-analysis from the Storm Prediction Center. The red lines are values of CAPE, and I'm just going to circle this one. This is 2,000 here across the central part of Illinois, and the inner contour is 2,500. So if you go to the Storm Prediction Center, it's spc.noaa.gov. They have a meso-analysis page, and it's awesome. You can see current CAPE and shear and all kinds of stuff, but this is just analysis from the past showing how we can view CAPE on a weather map. We mentioned that instability is fuel for thunderstorms, and the reason for that is the more buoyant the air is, the stronger the updraft can be. And what an updraft is just rising air in the atmosphere. In a normal thunderstorm, you have winds 30 to 50 miles per hour that go up. That is a normal thunderstorm. There's a reason why, if you look at a thunderstorm and the clouds go high into the atmosphere, those are the updrafts that you're seeing. With a true severe thunderstorm, notice the winds can be 50 to 70 miles per hour. And notice that's kind of a magical number because that is an updraft going up, but what goes up must come down. And so from those, we can get downbursts of up to 70 miles per hour, essentially a true severe thunderstorm. Supercells can have updraft speeds going up toward 100 miles per hour. When you have winds that strong going up into the atmosphere, that can support things like raindrops staying up above the freezing level and can certainly support large hail. The next thing we're going to talk about is moisture. We usually have plenty of this. We show this diagram or an example of this in our basic class. Our wind is from the south to southwest in the summer, so our air is coming straight out of the Gulf of Mexico, straight out of the Atlantic Ocean. So we've got plenty of moisture. The reason why that's important, it increases instability and it increases updraft strength. So both factors are important if you want severe weather. I thought this was a cool graphic, borrowed this from one of my previous offices that I worked at. A lot of us know that most of our atmosphere is composed of nitrogen. In fact, almost 80% of that. It has a weight of 28. The rest of our atmosphere, a lot of it is oxygen, luckily for us to breathe. That's 21% with a weight of 32. Water vapor is actually less than nitrogen or oxygen in terms of weight. It's much, much lighter. So the more moisture you have in the atmosphere, the more the air is lighter and it's going to tend to rise. And again, the greater the rise, the greater the instability can lead to clouds and eventually thunderstorms. So again, when moisture condenses to form clouds, heat is actually released. So that's another factor. This heat adds to the instability. So moisture is a big, big factor in thunderstorms, not just because you want rain and clouds, but it helps with the instability increasing and things of that nature. One way we measure moisture in the atmosphere is something called precipitable water. For the weather fans at home, we sometimes call this p-watts for abbreviation. This measures how much moisture in the atmosphere is above us in a column. We measure this in inches. Generally 1 to 2 inches is sufficient for thunderstorms. Greater than 2 inches can mean maybe not directly flash flooding per se, but that the atmosphere is primed. It has a lot of moisture, so we could at the very least get some heavy rain. If you spent any amount of time in the Carolinas, we are quite humid in the summertime, so our P watts can be high, and that's why we get those torrential downpours and things of that nature. And as a forecaster, we get a lot of information out of this. And what I mean by that, if the P watt is high, then we're concerned with flooding and things of that nature. So we've got some questions in the webinar, and I appreciate that. So I'm going to go through a couple of them now. We've got one from a Charles Bowen. He's looks like he's a weather fan here, and he's asking a couple things. So I'm going to answer a few of these, Charles, and then at the end I'll answer the rest of them. Let's see here. So one question, can you have rotation like a velocity couplet without a tornado? And the answer is yes. So what he's asking is, on a couple prior slides, we went over that you can have strong rotation, and that could be an indication of tornadoes. If it's high up in the atmosphere, or we don't have the conditions conducive to bring that rotation down to the ground, it won't be a tornado. So just because you have strong rotation, or what we call a couplet sometimes, doesn't necessarily mean it's a tornado. That's where our training comes into play. Is the atmosphere conducive to bring that rotation down to the ground? Is it far away from the radar, so we might be seeing rotation too high up in the atmosphere to produce a tornado? So great question for that. Let's see. He's got another good question. Is there ever an instance where insects on the radar can be a good thing, help seeing sea breeze on a clear day? Yes. So what Charles is asking is, sometimes we see those biological scatterers, and that can show us a difference in density, or to show us a difference in air masses across our area. So a sea breeze moving inland, we may not know that it's occurring if we were just looking for rainfall. But if we see those insects and other biological scatterers, we can see that. So those are really good questions. All right, so we're going to keep going forward. Again, if you've got any questions, please go ahead and ask through the webinar feature. I know I can't talk to you one-on-one in person like we could with a regular class, but we're trying to make this as interactive as we can. So we talked about P watts. This is an image of precipitable water. Again, this is from the Storm Prediction Center. This is a little clearer to see. You can see a P watt of 1.5 up across Northeast Illinois, and then values above 1 are shaded in green. So if you go to spc.noaa.gov, you can read the mesoanalysis page and see some of these variables in real time. All right, another ingredient you need, we talked about this in the basic class. Okay, you got the instability. You've got plenty of fuel. That's great. You've got the moisture. That's good too. But do you actually have something that's going to put it all together? We call this a lifting mechanism, kind of an acting agent to get everything going. And a lot of times we get this through things like cold fronts and warm fronts. We're going to go quicker through this because this was covered in the basic class. And then I'm going to jump into some things we didn't cover in the basic class, like sea breezes and mountains. So cold front is quite simply colder air coming in. It's noted by the blue line with the triangles, and the triangles point in the direction that the front's moving. Cold air is very dense, so it abruptly lifts the warm air in place upward, and they tend to produce the most vigorous storms. You can get cloud heights 50, 60,000 feet. A warm front is a red line on the map, half semicircles, and they point in the direction it's moving. In this case, the cold air is very dense. It's in place. It doesn't want to move. So as the warm air comes in behind a warm front, it gradually slides up over the cold air in place, and it's a more gentle slope. Can you have severe weather? Yes. Can you have a tornado with a warm front? Yes. But by and large, the storm is not as deep as what you would see along a cold front, and therefore the severe weather potential is lower. We went quick through that part. If you need more, again, we go more in depth with the basic stuff in our basic class. I want to jump to other types of lift. I know we don't have mountains here in Eastern North Carolina. Anytime, it's funny, I've lived here 3 years, and anytime I drive to just Raleigh, it seems like these giant hills compared to how flat we are here in Eastern North Carolina, certainly compared to what you see out toward Asheville or Boone, that type of area across Western North Carolina. So mountains, they can produce lift. They're a barrier. As air is pushed against it, it's naturally forced to rise. This picture on the right is beautiful. It's showing the air rising up over the mountains, and notice no clouds in the valley itself, but along the ridge tops you can see clouds. And we see this a lot on the satellite, often in North Carolina. Sometimes the first area that sees clouds bubbling up in the summertime is along the coast, along our sea breeze, which we'll talk about, or along the mountains itself, those barriers. Thunderstorms in general have natural outflows. We mentioned very, very strong updrafts that go up into the thunderstorm, 50, 70, 80 miles per hour. On the front end of the storm, the exhaust, that downdraft hits the ground. It's rain-cooled air, has heavy rain, gusty winds, and maybe some hail. As it pushes out, it acts like a mini cold front. These boundaries or outflows we call, they have cold air behind it. In front of them, warm air. Warm, moist air can lead to more thunderstorms. So these mini cold fronts can certainly increase the threat for thunderstorms. One additional slide I don't have, but I need to add for our local area. We see this, I'd say 4, 5, almost 6 days out of the week during the summer. Unless we have some type of strong wind to disrupt everything, we have sea breezes. That is caused by the difference in heating between the water and the land. The land heats up very quick. The water has a high heat capacity, doesn't heat up as quick. And because of that difference in heating, it actually causes a difference in pressure. The air naturally sinks high pressure over the water. The air naturally rises over the land since it's warmer, and things like to flow from high to low. So naturally, by late morning during the summer, our air flows in off the ocean. If you live in Emerald Isle, Atlantic Beach, Cape Carteret, this is why we tend to get breezy late morning through evening, and we tend to not have a lot of thunderstorms once that sea breeze goes through. Havelock, New Bern, Pelletier, Maysville. This is why you often see a lot of thunderstorms in the summer, because you're right along that sea breeze boundary. And again, it's like a mini cold front coming in off the water. We've got to add that to our presentation going forward, and we'll certainly do that. The last ingredient I want to talk about is wind shear. And again, I know this is a follow-up to our basic class, but I hope you see that we're just going much, much more in depth in terms of detail, and appreciate the feedback. I'm curious what folks think about this class as we wrap up here. I'll probably be in about 15 minutes. All right, so as far as wind shear goes, it's talking about a couple different types of winds in the atmosphere. There's directional shear and speed shear. The graphic on the left is showing that as you go up in height, which is represented by this blue line, you are increasing the difference in direction of wind. So you're starting off from the southeast and the south-southeast, and then eventually as you get up to this level, it's a southwest wind, and that is a difference in direction with height. The example on the right is speed shear. In this example, as you're close to the ground, indicated by this line right here, your winds are relatively light. As you get up in the atmosphere, notice how the line segment gets longer. That's an indication that the wind speed is stronger. So as you increase with height, you are increasing with speed. So if you're changing direction with height, or you're changing speed with height rapidly, that can induce a rolling in the atmosphere. And if that rolling or shear gets lifted in an updraft, that's where you can get some severe weather. And depending on how much instability you have combined with that wind shear, that will determine your type of severe weather. So, for example, on the far left, unorganized convection, we call these single cells or multiple cells. And we talked about this in the class. We've got some shear, or we've got some instability, but notice the shear is not that much. The winds are pretty light, and they're pretty much from the same direction up through about 10,000 feet. They differ higher up in the atmosphere, but by that point, it's too late. On the example on the right, we are kind of turning. We call this veering with height, and the wind speeds, these barbs, each tick represents 10 knots. So that's 40 knots, that's 70 knots. So we're increasing with height, not only the direction, but also the speed itself. And on the far right, we've got a lot of change in direction and change in speed. So we're going from a southeast wind at the surface, and as we go up in the atmosphere, this is indicating from the southwest, and we're increasing. If you have high instability, high fuel, and high shear, that's where you can get the organized supercells and the worst type of weather. Going back to the Storm Prediction Center website, I'll try to pull up the live view. I'm not certain about what's going on across the country, but we'll kind of go through it and maybe show you some real world examples. But a lot of times we look at something called 0 to 6 kilometer shear. This is a map of that. And if you look across central Oklahoma, this is an old one, we've got 70 knots of shear. Generally speaking, anything above 35 is favorable for severe weather, 30 to 35 knots. Again, it's not in a vacuum. You've got to have instability and a lifting mechanism and all that. You can't just have shear. It's like the recipe in your kitchen. If you're missing the eggs, those cookies or brownies are just not going to work out as well. Once you get above 50, then things get serious. And again, it's got to be combined with the right amount of instability to form those storms. This is a modified graphic from what we showed you in the basic class. We kind of simplified it: single cell, multiple cell, or supercell. And all we're trying to get across in this graphic is on the far left, single cell, you have the weakest amount of shear. But as you go from left to right, you are increasing not only the shear, but the instability. And if you think back to our basic class, how that helps is it tilts the storm. And with a tilted storm, as it's moving, say in this case from left to right, it can constantly get new warm, moist air and last longer. So this is our thunderstorm life cycle. The developing stage is where the updraft starts. You'll notice the 32-degree line is where it's below freezing, and above that, it's not a lot of cloud in this case. So this is just a baby storm. Our mature stage, this is where you have a full-blown engine. On the right, you have strong updraft going into the storm. This is the warm, moist air, 50, 60, 80 miles per hour going straight up. On the front side of the storm, which in this example is the left side, you have downdrafts, microbursts, descending air. This is your front side of the storm, the dark side of the storm where you have wind, rain, and hail. And that's as that air descends out of the thunderstorm itself. If you don't have a lot of shear, it goes from the beginning stage to the mature stage to the dissipating stage very, very quickly, 15, 20 minutes. By the dissipating stage, the downdraft is dominating, it's over with. If you have a multiple cell or even supercell, more shear, more instability, that life cycle may be hours, and it may take a place across part of a state. So they are more likely to produce things like wind and rainfall. One thing you can get with a true severe thunderstorm is what we call a downburst, a microburst. The strict definition is an area smaller than 2.5 miles is a microburst. It sounds fancy, but the air acts very much like a liquid. Again, you've got air rising in the atmosphere. What rises must fall. And as that air falls, especially if you get some drier air pushing it down to the ground, you can get some very, very strong winds. And this is a diagram of a downburst or microburst. As that air descends out of the clouds, it's going straight down. Right where I circle your impact area are your strongest winds. Then as you get farther away, in this case out toward the house or out to the far right-hand side of the screen, the winds are much, much lighter. So where the downburst hits, you can have wind speeds exceeding 80 miles per hour. We like to show this image because a lot of people see a lot of damage and they ultimately think it's a tornado, and that's not always the case. This is an example of hundreds of trees blown down. Again, to the average person, lots of trees down, had it been a tornado. But you can see the pattern is all in the same direction and divergent, flattened out. So damage like this is more consistent with a microburst and not a tornado. Again, you might say, well, hey, Eric, they're going in different directions. They are, but from the black arrows, or in this case, the yellow one, it's a divergent pattern. So it's either fan-shaped or flattened. That is more conducive of a microburst. We mentioned as you increase the shear, increase the instability, you're going to last longer. To go from the baby storm to the mature to the dissipating stage may take more than an hour, whereas a single cell may only last a short period of time. So your degree of damage is usually less because the storm just doesn't have long enough to maintain itself. An example of a multiple cell is a squall line. You can see the sharp reflectivity gradient. Anytime you see a line go from really, really bright colors to nothing out ahead of it, that's a good indication that it is severe, and probably wind speeds with it are the biggest issue. Often these lines are pushed at 50 miles per hour at about 5,000 feet. So again, it doesn't take much for a downdraft to translate that strong wind gusts down to the surface. Sometimes we call these bow echoes. Things don't happen in Mother Nature for no reason. The example on the left, I'm drawing, see how this reflectivity bows out? And that's because we have a rear inflow jet on the back side of the storm. Very, very strong winds are pushing that reflectivity out. So because of certain shapes on the radar, even without looking at velocity, we can determine that, hey, there's probably strong winds with that thunderstorm, because notice how it's bowing out. That's an indication of very, very strong winds along that axis. Here's an old diagram, an oldie but a goodie. This is a line of thunderstorms on the left. Again, I talked about that rear inflow into the backside of the storm. If it's very, very strong, what happens is it pushes that line out and you get this bowing feature. And again, if there's very, very strong winds behind it, that can bow the storm out and eventually translate down to the ground as a microburst or downburst of strong winds along the squall line. Now on the far right of this simplified graphic, the strongest shear, the strongest updrafts, the supercells. They can last the longest, most likely to produce tornadoes. Even if we don't get a true supercell a lot in eastern North Carolina, we can get them. And sometimes we get what's called a mini supercell, which has all the structure, all the characteristics, but the parameters such as CAPE and things of that nature just might be not as typical as you'd see in the textbook. Here's a diagram of the supercell. In this case, we're looking from left to right. So on the left side of the storm, you have this very, very warm, moist air going up into the thunderstorm itself. Very, very strong updrafts. And again, those wind speeds can excess 50, 60 miles per hour. This is where you'd be most likely to see your rain-free base, a wall cloud, and potentially a tornado. This is an idealized textbook going from left to right, the strongest updraft. That would be where your tornado would be on the back side of the storm. What comes up must come down. So the front side of the storm is your downdraft, or kind of the exhaust of the engine itself. I like to think of thunderstorms as engines because that's what they are. More moist air to support it, and then the exhaust is the front side of the storm. The dark side, where you see the heavy rain, the wind, the hail, the shelf clouds, and that's where you would see those strong downbursts hitting the ground, producing wind damage. So that's an idealized picture of a supercell. Bringing it to real world, look at the picture on the right. This is the Atlantic Beach EF1 tornado a couple years ago, 2018, bad year. A lot of us, of course, think about Florence, and rightly so. I still have neighbors that are getting their homes fixed from Florence. But earlier in the year, we had the winter storms. Of course, we had Florence in September, and then we had some tornadoes in November. So it was kind of a very, very wild year. The picture on the right is of a hook echo. This is the reflectivity, and it's just showing that that precipitation is wrapping back around. And then on the left is this diagram, what it would look like in terms of meteorology. Again, the rotation kind of wrapping back around, the circulation itself right there in the middle, co-located with the strongest updraft region. That is what the hook echo looks like on reflectivity to your right. So it's just about 10:48, a couple more slides, and we're going to wrap things up. You'll probably notice we aim for our virtual classes to be no more than 45 minutes. This is advanced, so it's going to be just a couple minutes longer than the normal one. We rate tornadoes based on a scale, the Fujita scale, based on damage. So we have a binder. We go out on a storm survey and we look, and whatever's damaged, that's what determines what the wind speed is. Is it a softwood tree? Is it a mobile home, a brick home, a strip mall, a hotel? This binder will give us a lower bound, an upper bound, and also an average, what wind speed would cause that type of damage. And based on that, we determine what the wind speed is. Based on the pattern is how we determine if it's a tornado or not. And we kind of went over that before with the divergent pattern being a microburst. The opposite would be a convergent pattern. So we mentioned this in the basic class. It's not how much is damaged. It's not how strong the winds are. That determines if it's a tornado. It's all about how is that damage laid out. In this example, you've got convergent trees. So notice how they're blown toward each other. And you can even see these scuff marks in the field itself. So that is a crisscrossing or convergent pattern indicative of tornadoes. So we're just about at the end here. Just a review of when you should report to us. Tornadoes and funnel clouds, you have got to confirm rotation. In the basic class, we kind of try to trick you with some scud clouds and things of that nature. If you see a low-hanging triangular cloud and it's not rotating, it is not a tornado or funnel cloud. Any size hail we want to know about, wind damage, flooding, heavy rainfall, especially if you've got a rain gauge that can help us out. To summarize our reporting procedures, again, this is only for Eastern North Carolina. If you're watching us from out of state or up toward Raleigh or Wilmington, your reporting procedures are the same. Who you are, what you saw, when, but you're going to use a different 800 number, you're going to use a different email, and we can follow up with your local office to ensure that you get that information. So that is it. I'm going to turn it over to you here in a second. I think that was pretty good, about 50 minutes. In-person classes tend to be a little longer because I can walk around, make sure everybody's still paying attention. The virtual one, we don't know what you're doing, so we want to try to keep it a little shorter than normal. That is my email address in the lower left. Depending on what you signed up with on your registration, you will be hearing from me with your certificate. So you can jot it down, but again, you're going to be hearing from me shortly with your certificate for the class itself. So I'm going to hop out of this. Just one more thing. Again, our SKYWARN schedule, weather.gov. And then if you / Newport, you go to the bottom of the page itself. Let me back up here a second. So weather.gov / Newport, you usually have a link toward the top. But if you scroll to the bottom, just click on SKYWARN. That page is always updated. We're in the off season. You'll still be able to find training. So we're in the process of putting our PDF and downloads up at the top. And then here's the schedule itself for future classes. But again, you forget when to report, it's right there. How to report, it's right there. Your neighbor wants to take this training. You know of a younger person that would be interested. Our YouTube training, it's right there. So that is for you. That is for you to take that training 24/7. So at this point, I'm going to turn it over to you for